How do we decipher the four atomic theories? Lesson 1. Do now. List 3 things you know about the atom. Well, hit pause. We'll come back to it in a few seconds. Okay, and we're back. What are some things we know about the atom? Well, the atom is very, very small, right? Small. Okay. Makes up the world, or makes up the universe. Okay, let's move on. So now, let's go over the atomic theory. Well, the first theory was developed by the Greek scientist Democritus in ancient Greece, and then later was taken over by English scientist John Dalton. John Dalton took over Democritus' theory, which basically said an atom is a hard sphere. So in other words, it cannot be divided. It was called indivisible. Cannot be divided any further. So Dalton concluded that an atom is hard, as small as indivisible particle. In other words, cannot be broken down to anything smaller. Divisible means can be divided. Indivisible means cannot be divided. Okay. So explain how the picture of bowling balls illustrates Dalton's theory. Well, if you look at a bowling ball, like over here, inside of it, the entire bowling ball's mass is filled. There's nothing empty about it. There's no empty space, so on and so forth. It cannot be divided any further. Thus, that's a perfect explanation for Democritus or Dalton's theory, which is called a hard sphere. Okay, pretty straightforward. Let's move on. Next theory is J.J. Thomson. Well, before I get to J.J. Thomson's theory, actually, let's go to it right now. J.J. Thomson was a student of Dalton. He was also an English scientist. He developed what's called the plum pudding model. That basically says that if you ever had plum pudding cake, it's basically like it's packed inside. It's a very spongy cake. Okay. Over here, they use what's called a cathode ray tube here. This is a cathode ray tube right here. Down highlight. Okay. There are two ends of the cathode ray tube. All right. So like in a battery, there's two ends. The positive end, which is a cathode. This is the positive. And the negative end, which is the anode. Okay? Now, when they passed the beam through the cathode ray tube, they found that the beam would bend towards the positively charged cathode. So they said, wait a second, hold on. There must be some charged particle that is in the atom, inside the atom. Okay? So, they're like, okay, well, if it bends towards the positive end, well, what do we know about opposite charges? Opposite charges attract. So they're going to name this the negatively charged particle, which is called the electron. So the electron is the negatively charged particle. Okay? And that's what happened inside that tube. Here's an example over here. All right, let me show you a little quick demo here. Okay? That I found. Here's a cathode ray tube that's going right now. Here's a beam of light. And you can just take a magnet or whatever, you'll see that it starts to actually bend the beam. Okay? So here's an example of the plum pudding model right now, actually. Let me show you quickly here. They have some great simulations. Okay? Now you see these little things floating by, those are called atoms. They have protons and neutrons. But actually, I'm sorry, the big ones floating by are called alpha particles. Alpha particles are large, positively charged particles. They're flying right by there. Okay, that's an example there. Try and make it max so you see it better. And this is a minimum now. So it's slower scale here. Okay, let's move on. Next thing I want to talk about over here is Rutherford's gold foil experiment. He used what's called an alpha particle gun. So here's a sheet of gold foil in the middle, like, right? We don't have gold foil normally. We normally have aluminum foil. And what he's doing, he's shooting the particles of gold foil. Now, if you notice, what is happening to most of the particles? Well, yes, most of the particles are just flying through. However, a small percentage of them do deflect. They'll deflect to the left, they'll deflect to the right, they'll deflect back. So now this also disproves Dalton's theory that an atom is a small sphere, hard sphere, because in fact, if you look at it now, since most of the particles go through, that tells you two things. That the atom must be mostly empty space. The second part of the theory tells you now that because it's hitting into something, there must be something inside or in the middle of the atom that's helping to deflect the alpha particles. That is called the nucleus. Now, from previous years, you probably learned about the nucleus, and maybe you even know about the subatomic particles in the nucleus. So in the nucleus, there are two subatomic particles. The zero charge neutron and the positively charged proton. And we'll learn that the positively charged alpha particles, when it hits a positively charged proton, well, if opposites attract each other, what do like charges do? That's right, like charges will repel one another. Here's another example of it. If you notice, most of the particles go straight through. Some of them get deflected left, right, some get deflected back. That proves that the atom is mostly empty space with a small positively charged dense nucleus. Okay? And I have it over here for you, okay? If you look at the notes over here. Rutherford's theory proves two things. Now, this is going to be on your regions. It always is. Atom is mostly empty space. The nucleus is small, dense, and positively charged. Okay? Here's an example over here. Here, the alpha particles hit the gold foil, and then boom. Most go through, some deflect back. Another animation would be another good one over here for you. I said before, but this time I want to do Rutherford's theory, okay? So let's press the alpha gun, the particle gun here. Here's your nucleus, the little yellow dot in the middle of the atom. The pink particles are the alpha particles that we said before. Now, again, what do you notice? First of all, there are 1, 2, 3, 4, 5 atoms there, right? Because there's 5 circles. And inside the atom, the yellow dot we said was a nucleus. If you notice, most of the alpha particles just simply go right through the nucleus. Simply go right through the atom. They'll bear to the left, bear to the right, so on and so forth. Okay? But once in a blue moon, they actually do hit them, and that actually scatters them back. Okay. That's a great, great illustration there. And that brings us to the last theory, which is a modern theory called the wave mechanical model, which is basically the electron theory. So in the middle of the nucleus of the atom, you notice that big red circle, and it has a positive charge. Well, which particles make up the nucleus? As I said before, the proton. According to table O on our tables, protons have a positive charge. And neutron. Well, think of a car. If you put the car in neutral and you're on a flat surface, are you going anywhere? No, you're not going anywhere because neutrons have a zero charge. So let's think a second, guys. Positive 1. What's 1 plus 0? Well, 1 plus 0 is plus 1. So the nucleus is positively charged. Okay? Now, if you notice this little red dot floating back and forth all around the whole atom, well, we don't exactly know where the electron is, okay? The electrons do not go around in orbit similar to how the Earth orbits around the sun. So the electron's bouncing from level to level at the speed of light, right? Let's think a second. Electron has the word what in it? Electricity, okay? Electricity has the word electron. So basically, electrons are electricity. And so what happens over here is that we do not know where the electrons are at a given level, okay? In fact, okay, electrons located in an orbital, right? Because it does orbit around the nucleus, not in an orderly fashion, though, we said. Not like, it's not like going around, like the sun, all right? But it's in what's called the electron cloud. Okay, this is the currently accepted model of the orbital. Orbital is the region where electrons are found. That's also found, this is also in the regions as well. All right, let's move on here. So here's some examples of what we went over today. Dalton's theory. We said Dalton's theory was basically the bowling ball. It's hard, small, indivisible particle. In other words, you cannot divide that. Well, we know that's not true. Then came J.J. Thomson, right? J.J. Thomson, the plum pudding model. All right, he discovered the electron. The proton, by the way, was already discovered by then, so we're not going to really go into that because it's not really necessary in the regions. All right, but the electron he discovered by putting a magnet at the cathode ray tube, he bent the ray down. Okay, we know opposites attract, like charge repel. Next came Rutherford. Rutherford's Goldfall experiment basically says what? An atom is mostly empty space. Inside the atom is a small, dense, positively charged nucleus. Okay? And over here is a Bohr's planetary atom. You really don't need to know this. Not in the regions. And this is what we did right now, the wave mechanical model or the current orbital atom. Again, the electrons are flying around the electron clouds at the speed of light. We don't know exactly where they are. All right. So that is